is Drew Kessler, and he's joining us electronically this morning. He's up in Maple Grove, Minnesota, and didn't feel free to make a trip down I-35 tonight. There's quite a bit of warnings about complete ice-covered portions of I-35. He's a senior scientist with Houston Engineering, focusing primarily on integrating science and technology into decision-making for water quality. His presentation will be using technology to fill information gaps of BMP benefits, using on-the-ground implementation and large-scale planning efforts. Let's take it away.
Thanks, Brian. And if you guys have any trouble hearing me at any point during the presentation, please do maybe poke Brian and have him jump in front of the screen and tell me to adjust as needed. As Brian indicated, my talk today is going to be basically on the integration of science and technology. In particular, I'm going to be focusing on a project that we completed in Minnesota called the Prioritized Target and Measure Application. And really the way I presented the abstract for this talk was that we developed, or at least helped develop, some technology that can help break some of the gaps between watershed planning and local implementation. So what I'm showing on the screen here is pretty Minnesota specific. I have on the screen on the far left side, and I'm not sure if you guys can see my mouse pointer or not if I move it around, but on the far left side I have TMDL wraps, which in Minnesota get done at a fairly coarse scale, about 8 watershed scale. Then I have in the middle local planning, which is governed by our State Board of Water and Soil Resources. And then on the far right side, local implementation. And the general idea here is oftentimes there are models or analysis run at coarser scales for these coarser scale studies that don't necessarily trickle down to inform local implementation, although ideally they would. And similarly, sometimes things that happen at the local implementation scale, at least the things that get put on the ground, that information doesn't always get aggregated up to inform progress towards those larger scale planning efforts. Now, I realize that right now I'm presenting for an Iowa Water Resources Conference, not a Minnesota Water Resources Conference. But I do think the examples I'm showing here today, which were done in Minnesota, are transferable to some of the work that's being done in Iowa. So what I did is I just basically switched out some of these titles for the work, at least my understanding of the planning structure that occurs in Iowa. So at the coarser scale, you guys have developed nutrient reduction strategies. You also, which are, I believe, at a fairly coarse scale, at a state scale even. And then you also have kind of somewhat finer scale planning efforts that occur at maybe a 12 to 10 scale through IDAL's water quality initiatives. And then there's also local implementation. And so the idea here is we can use technology and a lot of the data that's available today to make sure that the planning that occurs and local implementation that occurs is kind of communicating across these scales. Now, backing up a little bit here, the reason this project was developed really was for Minnesota-specific business needs. In particular, business needs of local government units, mainly soil and water conservation districts and watershed districts. In Minnesota, we have the Clean Water Accountability Act that was passed a few years ago that has basically put the burden on local governments to show that any state dollars they go after to implement conservation practices are prioritized, targeted, and result in measurable water quality improvements. So it's putting a burden on local governments to produce more information about the intended way they plan to implement conservation efforts. Paralleling that, or coming online around the same time, is something in Minnesota that's being called the One Watershed, One Plan. And basically what that is an effort to unify local water plans around the watersheds, at watershed boundaries, at HUC-8, essentially watershed boundaries, as opposed to how they've been done in the past in Minnesota, which is based upon local jurisdictional boundaries, so county boundaries, which, as everyone in the room knows, oftentimes do not line up with watershed boundaries. So because of these two things coming online, there was a bit of a business need recipients to have access to technology that can help them produce the information that's needed to satisfy the Clean Water Accountability Act and aid in planning efforts in things such as a one watershed, one plan. So because of that, it was actually our State Board of Water and Soil Resources that hired the International Water Institute, and I'll get to this on the next slide, to develop the Prioritized Target Measure application, or PTMAP. And essentially what PTMAP is two components. It's a desktop toolbar. It's free for download. Once again, this was funded with public dollars, so everything I'm showing here today is actually owned by the state of Minnesota, not Houston Engineering. I'm just going to here present it today. So there's a desktop component, which is an ArcGIS desktop toolbar. This is really the engine that generates all the data and does all the analysis that I'm going to be presenting here today. And then once that information is developed, there's a web component, which it says final testing here. It is kind of beta released at this point, but it is up on the web, and anyone who wants to go take a look at it can. PTMAP web component takes the data from the desktop and puts it in a more, I would say, user-friendly interface that even someone with non-ArcGIS skills should be able to look at and use. So I mentioned there was a project team for the development of PTMAP, and this is just kind of laying out how that looked. The entire project was funded with Minnesota Clean Water Fund dollars, and I think most people in Iowa at this point are aware of what our Clean Water Fund is. If not, go ahead and ask a question at the end. The dollars were allocated by the Minnesota Board of Water and Soil Resources to the Red River Watershed Management Board. The Red River Watershed Management Board brought on the International Water Institute, which is located in Fargo, North Dakota, to be their prime contractor to develop this project. And Houston Engineering, who I work for, was hired as a subcontractor to help with some of the technical work. So what I'm going to do for the rest of the presentation is basically walk through some of the different products that can be produced by running PTMAP. And what I'm going to do is show examples of how data was generated for the development of the Root River One Watershed One Plan using PTMAP. And what you're seeing on the screen, these different boxes, the green, red, blue, yellow, and gray colors, are different products, are symbolic of different products that can be produced by PTMAP. And also what you're seeing is a little two-page summary that was developed by Bowser, the Minnesota Board of Water and Soil Resources, to kind of give a big picture overview of what the toolbar does. And so what I'm going to spend most of the remainder of the presentation doing is walking through some of these different boxes and showing how it relates to filling some of those gaps in watershed planning and arriving at a targeted plan that has specific practices on the landscape that at least have estimated water quality benefits for downstream resources. Oh, and I should mention, I'm not going to go into much of the theory for PTMAP. I am going to show, sorry about that, I had a phone ring in the background here. I hope you guys didn't pick that up too much, but I am going to show some of the theory for some more novel development that we did, particularly for how we estimate water quality benefits. That being said, all the technical documentation for PTMAP is available online, and I'm going to be showing the website for PTMAP where all that information can be downloaded at the end of the presentation. So the first box that we're on here is called Describe. So anytime you go through a watershed planning effort, one of the first things what's typically done is you basically need to describe the current condition of your watershed. So one of the things that's packaged with PTMAP for Minnesota is a bunch of public data that gets set up to clip towards your watershed boundary. And the general idea with that is once you start running the toolbar, you'll have all the information you need to begin describing the current condition of your watershed after you've begun running the desktop toolbar. And what I'm showing on the screen here in this map, and I apologize, again, I can't see the size in the presentation room to see if it's clear, you can make out the graphics. But what you're seeing is the south fork of the Root River. The yellow line towards the bottom of the map is the south end of the plant boundary, which actually goes straight south into Iowa. So we are right on the Minnesota-Iowa border here. I should also mention that this plan, the plan I'm going to be describing here, the Root River 1 Watershed 1 plan, is in draft stage and it's going through local review right now. So everything I'm showing you here today in terms of the way the maps look and the data and everything else is draft and may be revised as it goes through the local review process. But anyway, the purpose here is that in running PTMap, you're going to have a bunch of packaged data that's set up for your study area, whether it's a whole Huck 8 watershed or what I'm showing here, a Huck 10 watershed, the South Fork of the Root River. So you can begin to describe your watershed, or basically come up with the current landscape condition of your watershed. One of the other things we go through in Minnesota, and I think this gets done in Iowa as well, is local entities have to decide which resources they're going to manage. The reality is that time and dollars are limited, so you can't get everything done that you might want to, particularly within one plan cycle. So one of the processes we go through in Minnesota is resource prioritization. In other words, laying out all the different resources that are on the landscape, and then making decisions, usually done by locals, the local governments that are involved in the plan and responsible for implementing it. We go through the process of actually ranking and prioritizing which resources they're going to work on. And so the kind of messy map you see here is just an example of some of the data that was captured when we did this running PTMap. And it's basically points on a map where some of these different resources those locals might want to manage are located. And so this next box is completing source assessments. And what you're seeing on the map, and again, I apologize, I can't see if this is displaying very well on that end. On my end, it looks a little fuzzy actually. But what you're seeing on the map, again, is the South Fork of the Root River. And once you've established your resource priority points, or those points on the map where there's things you want to manage, you can then run PTMap to get an estimate of how much sediment, nitrogen, phosphorus get delivered to those points on the landscape. And that's basically what I'm showing on the map here. The green dots are the actual points that got put in. Those are the points where PTMap is calculating load estimates. And what you're seeing in the shades of green are what we call catchments. So underneath all the data I'm showing today is 3 meter by 3 meter LiDAR data. One of the processes we went through in the development of PTMap is what we called a series of blue ribbon panel workshops where we basically got together with 20 different soil and water conservation district staff from around the state and showed them information that could be generated by a toolbar like PTMap. And they gave us guidance as to how that information would be useful for their businesses. And one of the things we were told is that they didn't want to see a bunch of raster maps or 3 meter by 3 meter maps come out of this. What they wanted was to have that information aggregated at a coarser scale. And so that's why you're seeing more of a polygon layout here, and that's what we call our catchments, which are field scale representations of the landscape. They average in size about 40 acres. And you'll be seeing, the reason I went into so much detail on that is you'll be seeing these catchments on several of the maps I'm going to be showing for the rest of the presentation. Anyway, what you're seeing specific to this map is darker green areas represent areas that have higher total sediment loading to outlet this Huck 10 watershed, or the outlet of the South Fork of the Root River. So, in other words, the dark green areas are sending more sediment to the outlet of the Huck 10 watershed. Same information can be generated for nitrogen and phosphorus. The next step that's built into PTMap in terms of the data that comes out is estimates of where potential practices can be placed on the landscape. And so what you're seeing on this map are locations of where different practices have the potential to be placed on the landscape. The techniques behind doing this are basically based on the NRCS Field Technical Guide. So we look at the information for particular kinds of practices and did our best to estimate where those practices could be placed on the landscape based upon topographic characteristics. So once again, on top of the LiDAR data essentially, and land use land cover information. And because we know where potential practices could be placed on the landscape, and we know where the sources of sediment, nitrogen, and phosphorus are coming from, what we can do with PTMap Desktop is combine that information potential water quality benefits of those practices would be in terms of load reductions in sediment, nitrogen, and phosphorus. And we do those estimates both at the practice location and at those downstream resource points. So what you're seeing laid out on the map in front of you here is the potential sediment load reductions for at these different catchments relative to those at Huck 10 outlet point, or that priority resource point I showed on the map of the whole slides earlier. So in other words, the darker green areas are the areas in this Huck 10 watershed that have the highest potential to provide a sediment load or large sediment load reduction at the outlet of the South Fork of the Root River. And now I intentionally have a pretty big shift in the PowerPoint background there, and I should have 2 points in the presentation where I did this being one of them. The reason being is, instead of looking at some of the output products, this is one of the sections where I'm actually going to go a little bit into the background of how the calculations are being performed. And what I'm going to highlight over the next several slides here is how we actually estimate the efficiency of a practice inside of PTMF. So I'm going to be giving you at least a little bit of a background about how some of the calculations are performed. And what you're seeing on the slide right now is how we group potential BMPs into different, what we call treatment groups. And you're seeing 6 of them in the column headings across the top. And it does look, I apologize, it does look like the slide formatting bunched up my columns a little bit, but they are storage, filtration, biofiltration, infiltration, protection, and source reduction. Now the reason we group practices this way is because there are quite literally hundreds of different conservation practices that could be put on the landscape, and it's really just not feasible to model all those or estimate where they could be located. So instead, we group them into what we call treatment groups based upon the primary form that they provide treatment with sediment, nitrogen, or phosphorus. And essentially what we do for all these efficiency estimates is use what we call a reduction ratio. And I'm going to show what that is in the next couple of slides here. So basically, for every potential practice on the landscape, and what you're seeing on this slide is an example of where we identified potential locations for filter strips, we estimate a volume of water or a peak discharge of water delivered to that practice. And we ratio that to the potential treatment that that practice can provide. The idea being, if a practice can treat 100% of the water it sees, it should be more efficient than a practice placed on a point in the landscape where it can maybe only treat 10% of the water it sees for a given storm event. And the general theory looks like this then. What we do is we insert that reduction ratio into a first order decay function. And the general idea being, and these Q statistics are based upon the empirical distribution of the effectiveness of different practice types that we've taken from the literature. And the general idea is, if we put in a reduction ratio, let's say it's 50% at the center of this graphic, and the majority of practices have pretty high treatment within that group, you should probably, at that 50% treatment, have a slightly higher efficiency at that BMP. And this is what it actually looks like when you put that into the data that we've shown on the previous slide. So this is, and I apologize, it looks like my slide got squished a little bit again there. The sediment reduction efficiency, this is percent reduction for the filter strips I'd shown. And what you're seeing is spatial variability in the effectiveness of these practices based upon where they are in the landscape. And it's driven by 2 things again. The amount of water it sees relative to what it can treat. And that ratio is used based upon empirical information on how effective that practice is to scale the efficiency of the practice. And what this enables us to do is to account for things like design uncertainty and maybe just bad timing when you put practice in. If you put a filter strip in, seed the grass, and then you get 2-3 inches of rain right afterwards, your efficiency is going to go down quite a bit. So not only are we estimating a spatially variable effectiveness, we're also building statistics that help us account for uncertainty and how much treatment would occur. And so at this point, we have information that allows us to work with locals to pick the best locations for practices to plan implementation. And what we did in this instance of the Root River is we picked 100 of what we consider the best practices based upon their absolute load reductions in sediment and nitrogen in each Hub 10 watershed. So it's been hard to make out the map, but within the South Fork, the Root River, we had around 100 practices. And the note on here, so one of the things we're not able to account for, because this is a desktop analysis, is the location of existing practices and whether or not the landowner where we're saying there's a potential for a practice is actually a willing participant. So we're not taking account of existing conservation, and we don't know whether or not the landowner in that location is willing at this point. This is still a planning exercise. And then what we do is we run that through something we call a treatment train analysis. So the earlier information I showed you on BMP load reductions was only considering an individual BMP on the landscape. It wasn't considering what may be a series of BMPs in sequence where the load one BMP sees is already reduced by an upstream practice. So I'm going to go into the methods behind that, but when we run that analysis, what we get, because we have these priority points where we're getting information, we get load reductions for that implementation scenario at multiple points on the landscape. So these different sub-watersheds line up with the names in the table at the top of the screen, and I would guess if the room's fairly good size, you might have a hard time seeing the numbers on the screen, and I apologize for that. But basically what it's showing is from those 100 practices I showed on the previous slide, different load reductions at those priority resource points that the locals want to manage for. And this is just a little bit of a background on how those treatment train calculations work. And I apologize, there's a lot of equations on the screen here, but I am going to click forward a little bit to get to the graphical representation of how this works. So here's another little example, and this is still within the Root River watershed. This is the Middle Fork instead of the South Fork. But what you're seeing on the screen is a catchment with the black outline. The blue crosshatch is a filtration practice for what would probably be a grass waterway in this instance. And the red outline would be some sort of infield management. And what we do inside a PTMF when you run a treatment train analysis is we apply that treatment to a watershed, the contributing area of the different practices. And what that allows us to do is to stack these efficiencies on top of one another. So the filter strip is providing a 76% reduction in the light green area. The source reduction practice is providing a similar reduction in this instance, although that would vary in some areas, 76% reduction in the black area. And underneath that, as I mentioned towards the beginning of the presentation, we have this LiDAR information on sediment sources. And so what we're able to do is multiply these all together, and the bottom of this shows how that sediment, that raster is reduced by the efficiencies of the BMPs on top. And so when we sum that all together, that is how we get at the load reductions for the treatment train process. So I think I'm getting close to my time here, and I did want to leave at least a couple minutes for questions. So I have a few final thoughts here. Some of the things we haven't done with this yet, but is possible because we have uncertainty built in, there would be the potential to look at different storm events to use this tool to estimate how climatic variation might impact the efficiency of your BMPs and in turn the performance of those BMPs as a whole. One of the other things I didn't get a chance to touch on is we do some hydrology calculations based upon the present landscape condition inside of PTMF. One of the things that people could do, and this is something that's a very hot topic in Minnesota, I believe it's a topic of interest in Iowa as well, is look at how modern discharges vary relative to historic discharges. So what I'm showing is a little sample analysis we did for the Middle Fork of the Root River. And what we did is we used pre-settlement vegetation to look at historic discharges, peak discharge for a 10-year, 24-hour event, and compare that to modern-day discharges. So the dark blue areas have 100 cubic feet per second greater peak discharge today than they did in the past. Another thing, I'm just kind of throwing ideas out here as to how PTMF is being implemented in Minnesota. We have something called the Governor's Comfort Law. That's not the official name of it. But one of the things we're using it for in Minnesota is to help develop a framework for how landowners for specific fields can consider alternative practices to buffers. And so what you're seeing is a layout of an output from one of those projects where farmers, if they want to put a buffer in, can, or if they do the calculations we're suggesting here using PTMF, they can look at other practices in that so that they might be able to use that practice, or at least have some options for using that practice as an alternative to a buffer. Some of the limitations of PTMM, we do have some fairly large processing times, and this is just a brief summary of limitations. We are limited by the spatial resolution of land use and land cover data, which in most areas is just a 30-meter grid cell, so that does impact our calculations a little bit. To this point, basically most of our calculations are empirical. We are just starting to work more into validating some of the data you've seen today, and we do need to do more validation of the results. As I mentioned, it ignores existing practices unless a user puts them in. It does not do species of nitrogen or phosphorus, and everything I showed you today is for overland sediment, nitrogen, and phosphorus loading. We do not have near-channel sediment calculations built in, and we do not do hydrologic routing at this point in time. I do like this quote right before I kick it over to questions here. George E.P. Box, essentially all models are wrong, but some models are useful. Really the purpose of PTMM is not to come up with a new way of doing source assessments or finding out where the bad actors on the landscape are. Really the purpose, the business need is to help provide information, to help inform better options for where conservation practices could go on the landscape. In other words, give people more options for where conservation can go and then communicate that back to higher level planning efforts. And so with that, the website is on the slide here, and I'll be happy to take any questions if I have some time left.
Yes, Drew. Brian Geller is back here.
Hey.
We do have a little bit of time for questions. I can relay those questions if you want to come up here and actually ask them to here. If you want, Arcade.
Talk about how you enter the practices, and if you could like throw a shapefile or a database with electrical practices.
Okay, how do you enter practices into PTMM? Is it a GIS type interface, or what? How are practices entered into it?
Great question. Well, the user has the option to put their own in, and it is an ESRI ArcGIS interface. It's an ESRI ArcGIS desktop toolbar, and you would simply put those in as a polygon shapefile, and you would have to insert some formatting in terms of the attribute columns that is documented in PTMM. Now, in terms of all the practices I showed today, those are outputs of the toolbar. There's a BMP suitability button that estimates the locations where practices could go on the landscape.
Yes.
Yeah, obviously this was created to fit the data that you have in Minnesota. I just was curious as to how that might be adapted. If we wanted to use some sort of plan tool like this in Iowa.
Yeah. So just the question: how would you adapt this to Iowa? Do you have any insights? Because this is somewhat fit to Minnesota data. What can you see as being required to do a similar process in Iowa?
Yes, it could be fit to Iowa. We're actually going through the process. This is a lot of what I showed you today is Minnesota specific. That's 100% right. But we're actually in the process right now of adapting the entire toolbar to North Dakota, and we're making pretty good progress on that. So a similar process certainly could be used to adapt it to Iowa. The biggest hurdle would be what we call a base data catalog, which is all the public data sets that are Minnesota specific. That would have to be developed for Iowa. And then the second part of that would be you would probably want to go in and check some of the yield coefficients that we use for nitrogen and phosphorus. And you would probably want to double check against Iowa data the efficiency of the practices.
All right. Hold on.
So for like, as far as the time frame goes, I would assume you have to use a hydrological modified LiDAR. So is that each line through Houston Engineering, and then from that forward, kind of like what's an average timeline for like about 12?
All right. So a little bit on timeline. So you just
parcel. And then you also need inputs or composed soils data, but that's just typical soils data, which is nationally available. So the short answer is yes, you would want a hydro modified